Thank you all. So, good afternoon everybody. My name is Pierre Audier and I work as a data scientist at SNCF Rolling Stock Engineering. And today we'll talk about condition-based maintenance for complex systems through the example of passenger access. I will be as short as possible to keep the time with us. So, first, small introduction about maintenance and its optimization using data, big data. Here is a video about maintenance with subcategories. So just to be short, the goal is to optimize this to have gains on reliability, ownership costs, and customer reputations. So the preventive classical scheduled maintenance is often organized like this. So from the delivery to the decommission, you have inspections, and those inspections are realized with a frequency depending on the operational days or the distance traveled by the train. Then each inspection could be divided into few tasks. And at the end, okay, you have a check, repair or not, and then, okay. So we have to optimize this process, but actually this is the view. So on this figure you have the health indicator value, meaning the level of degradation of the system, plot against time. Here is the point that from the delivery to the decommission, you have inspection, and you have only a vision of your system during inspection. Out of or between inspections, you are totally blind. You have an unknown state of your system. So sometimes, okay, the inspections, it's okay. You have the level of degradation which is just above the preventive threshold. So okay, during the first inspection, there is a reparation and it's okay. But sometimes there is no need in reparation. So only the second inspection is really useful for the system. So here is the problem. We have to optimize this. And hopefully, we have a new generation of natively communicating trains, which arrived in Paris and suburbs since 2010. So at the date, we have 250 trains communicating a lot, a huge amount of data and contextual information. So we are using all this data to optimize the maintenance at SNCF. So the first thing is important to identify the maintenance task that can be realized, delayed, or purely suppressed using real-time monitoring. For instance, you can measure the distance between the two panels of the door during the opening, or you can measure the tension of the belt. So the first question is, from the task, is it possible to perform this check with real-time monitoring or not? So if it's not possible, you can use the classical preventive schedule maintenance. And you can optimize it with reliability-centered maintenance. However, when it's possible to do this with real-time monitoring, you can do predictive maintenance using with condition-based maintenance. And both of these maintenance and optimization will lead to the whole maintenance optimization. So now the view has changed. You have a full vision from the delivery to the decommission. And now you can adapt maintenance from predictive or reactive to corrective. And you have a choice to do a task when you want or not. This is the theory. So, following this way, SNCF Rolling Stock has developed a maintenance strategy which combines both preventive scheduled maintenance and corrective maintenance. So basically, you have training operation, you have the preventive maintenance process, and you have also the corrective maintenance process. So, however, it's almost impossible to completely replace preventive inspection by predictive maintenance. For instance, you have visual inspection, you have lubrication to do on trains. So it's not possible to fully replace this. So we choose to put some predictive methods into this process. So when your train in operation can be monitored in real time, you can do some prediction and some condition-based methods. With condition-based methods, you can have two kinds of orders. So orders of repair or just maintenance order. One is going to the preventive maintenance process, and the other one goes to the corrective maintenance process. And all of this is fully possible using a whole data workflow. So just to be short, we have several parts of this workflow, from the data definition to the presentation of the data. We gather data from onboard train system. We order and link data together, we analyze data, and then we transform or translate data to maintenance orders or operation orders. And all those information has to be gathered and displayed in industrial tools to help maintenance operators or maintenance schedules. We have a special part with analyze, where we analyze the data. So sometimes we talk about AI or machine learning expert system. So in case of passenger access, we are using expert system. So basically, we have a huge amount of data. So more than 250 trains. Each train has 16 doors, opening a few times a day. So a huge amount of data. And we have also experts of passenger access, who brings knowledge into data scientist algorithms. So at the end, we have health indicators created by data and experience, field experience. We are not using kind of machine learning or black box to get an algorithm to create those health indicators. About health indicators. So, few definitions. We talk about the step from raw data to the design of health indicators. First, you can say that failure can be defined as gradual alteration of the nominal performance of the system. In case of a complex system, such as passenger access, it's really essential to understand the underlying physics of the system, to use the field expert who knows exactly how works the door, steps, etc. But first, just before the commissioning, we test passenger access on a scale model or on test trains. This step is really essential to perform experiments, to test reliability, to test the data integration, and to get a precise map of the performance degradation of the system. Here you can see an example of sliding steps. You have a lot of sensors everywhere. And at the end we say, okay, we can have information and extract this information to say, okay, we have a problem here with an end stop or with the tension of the chain or bed, etc. So, the raw data available, we have for the passenger access all the input and output information which are circulating through the train network. So, all these informations are processed and recorded on board, and then are packaged and then sent to the wayside. For passenger access, we have different kinds of data. We have contextual data, we have logical data, and also analogical data. Something which is really important also is the sampling of the data. Because you can choose the sampling before the data will be sent from the train to the wayside. And we have to specify the sampling as the sampling rate is sufficient to perform computation or analyze, but not too big to just expose the size of the farm. Not to have data to have data, just to have essential information. After getting the raw data on the website, we are pre-processing the data. So For instance, for passenger access, we can define cycles and sub-cycles. When a train stops at a station and the doors open and close, we can have one cycle. And this cycle can also be cut into sub-cycles. You have the unlocking of the door, the opening, the closing, and locking. So four sub-cycles. And each sub-cycle can perform specific computations. Something which is really important is the filtering. For instance, passenger access systems are mechanically sensitive to the elevation gradient of the truck. You can imagine that a motor needs more or less current to open a door or a sliding step, depending on the inclination. So we have to filter those cases to only keep interesting cycles for our computations. So here is an example. In case of passenger access, during the opening of the door, the panel slides outwards and the friction forces are decreasing as a function of time. So here you have the current of the motor plot against the time. In the blue cycle, you have the area of interest. And this part refers to the mechanical adjustment of the sliding steps. And by only doing simple mathematics, as using linear regression, we can have two health indicators as A, the slope, and B, the y-intercept. And with those two health indicators, we can have information about the adjustment of the sliding step. So it's not so complicated, but we need experts on the system before defining all this. So, after defining health indicators, we also create a new kind of signaling systems based on remaining useful life. So the specific system is both based on preventive and corrective maintenance. We combine all of them. So at the beginning we have health indicator, and this system can switch between preventive maintenance to corrective maintenance, depending on the evolution of the data indicators. And now this is the new view. So the blue part on the left of the graph represents all the measured data. So we know all what happened before this part. And the orange part on the right, just prediction. So with this we can adjust model. And now we have flexibility into maintenance. We can say, okay, maybe the remaining useful life is 7 days, so I can take over the train tomorrow, or in 5 days, it's gonna be okay. But if I have the opportunity to do this before, I can do this because I have this view. So as I said before, we also need to gather all this information for the management of the maintenance, for the schedule of the maintenance. So here is an example that we created for the management of train in Paris. Here is the whole fleet of the train. One square represents the train. The size of the square is a function of the time needed to repair the train on the specific system. And the color is proportional to the level of degradation. So with this, we can say, okay, this one is more critical than this train. And we can organize more easily the maintenance. We have also special rules for those with a specific maintenance task. But what is more interesting is now we can perform connected traceability. So before the maintenance steps, the maintainer will say, okay, here are all the tasks that I should perform on the train. If the whole traceability is great, there is no need to take over the train for this operation. And this maintenance operation should be postponed. In this case, when you have rest process, now the time needed to repair the train is strongly reduced because we only have to check where the red processes are and to repair the check the system and repair the system. When it's green, no need for verifications. So the time is really reduced. this also brings the opportunity, as the time is reduced, to do some opportunity maintenance. I know that on another system, I need to replace an end stop or a sensor. I can do this during this operation. So this is reality for those trains now in Paris. So moreover, we are doing the same thing for compressor, battery, photograph, HVAC systems, toilets, and maybe next year we will perform this on traction and brakes. But it's more complicated because it's directly related to the safety. So more time to do this and to implement this into the management of the maintenance. So as a conclusion, SNCF will set a new maintenance system based on real-time monitoring of the system for passenger access and data analysis. So here is the whole cycle of the data workflow. And just to conclude, we perform a solution for passenger access in evacuation with the rolling stock lift constraints. And now we have data analysis, scheduling helper, native connected trains, and maintenance center. And at the end of this, our solution is completely turnkey for SNCF because it was designed for the SNCF maintenance system. And this is optimized without breaking the existing system, the existing maintenance system. So this is a huge step for SNCF into the maintenance. So that's all for me. I think I'm pretty on time. So if you have any questions, we can discuss later. Thank you.